Okay, second example. Instead of Ka, we're going to do Kb. So calculate the base dissociation constant Kb at 298 kelvins for 0.00100 mole per liter solution of the base C6H5CH2NH2 phenylmethylamine. The pH of the solution is 10.17. In this example, I found it handy to include the water, even though in the previous example I didn't. And that's because I wanted to show you where the hydrogen went from the water. So remember, in water, you got hydrogen ions and hydroxide ions. Water in this case is your base, and that water is going to donate 1 proton to your phenylmethylamine, and that's where you get the NH3 with the plus, and the water missing its hydrogen with the OH minus. Base, acid, conjugate base. So let's write in what we know. So we are given a 1 times 10 to the negative third concentration of your phenylmethylamine. So I'm going to put that here, 0.00100. And initially, I'm going to have none of the conjugate acid, and I'm going to have none of the conjugate base. I also know that this is still a 1 to 1 to 1 to 1 ratio. And I'm not including water in my ice table because water is your solvent pure substance, and pure substances do not have a concentration. So my phenylmethylamine will lose X, and my conjugate acid will gain X, and my hydroxide ion will gain X. And so I need another piece to the puzzle, and that's going to come in the pH of this solution. Now, unlike the last example, there's one more step we have to do with this. We have to remember we're calculating Kb, and Kb is your base dissociation constant. So we can't use pH, we have to use its brother POH. So I can get that really easily because I told you in the past that pH plus POH equals 14. So if I know that my pH is 10.17, I can easily find my POH by subtracting. And so I'll find that my POH in this case is going to be 3.83. So if it's very basic, I should have a very low POH. And then I can do what I did before, and I can find the antilog of this and say 10 to the negative 3.83 is going to be my concentration of hydroxides. Plugging that into my calculator, I find that my concentration of hydroxides is going to be 1.48 times 10 to the negative fourth. So that's what my equilibrium concentration of hydroxide is. That's going to go here. Since it's a 1 to 1 to 1 ratio, it's the same here. And now I'm ready to figure out at equilibrium how much phenylmethylamine I have left. So I'm going to erase this piece here. So now I'm ready to get my equilibrium concentration of the base I started with. So I'm going to go 0.00100 minus the 1.48 times 10 to the negative fourth. And I know x is 10 to the negative fourth just because of my equation here. 0 plus x equals this. So I know x has to equal 1.48 times 10 to the negative fourth. I'm going to plug that into my calculator. 0.00100 minus parentheses 1.48 times 10 to the negative fourth. And I find my equilibrium concentration is 8.52 times 10 to the negative fourth. Again, barely any of the original concentration dissociated, but more so than last time. So now I'm ready to get my Kb value. So again, my Kb expression looks a lot like the Ka expression. Products over reactants. So here's my conjugate, C6, my conjugate acid, C6H5CH2NH3. And then there's my base. And then my original acid. You might see a pattern going on here with dissociation, that you will always have the same molar ratio of 1:1 in your products. So you're going to see here that this is going to be 1.48 times 10 to the negative fourth squared, all over my 8.52 times 10 to the negative fourth. Solving that all out, I get something in the realm of 2.57 times 10 to the negative fifth. And if you followed me on the last example, the units are going to remain the same, moles per liter. I want to take a moment here and talk to you, however, about what we call the 5% rule. And the 5% rule has to do with whether or not we have a valid Kb value for this particular situation. So what they're saying here is this: the change in equilibrium from your original concentration cannot be more than 5%. So our change in concentration, what we had before was, let me get back to my pins page here. My change in concentration was the 1.5 times 10 to the negative fourth. My initial concentration was the 0.00100. And when I calculate this out to find a percentage, you're going to find that that's 15%. What that's telling me is that too much of the acid dissociated, and that means that since this is a weak acid, we know that the measurements that the scientists took have to be incorrect. Maybe the temperature was not 298 K, maybe it was hotter, maybe it was cooler than what it was supposed to be. So IB doesn't test you on this, but they do want you to notice here that these calculations aren't set in stone, and they're still all approximations, and there are double checks for this. This particular calculation here is considered invalid because it is 15% higher than what it should be. It should be within the range of 5%. Again, that's just something to mention. It's not something crucial that you need to lay down and know completely. So here is your Kb calculation.